This is part 2 of the lecture on the spherical Earth. Specifically, this is for Conceptual Physics AB. In part 1 of this lecture, I went through the observational evidence that we have that in fact the Earth is a sphere. The observational facts that I went through, they definitively prove that the Earth is spherical. The next immediate question then therefore becomes the following. If the Earth is spherical and is then therefore of finite size, how large is the Earth? Well, the first person to definitively answer this question and arrive at an accurate result lived around the time of the ancient Greek culture that I mentioned in part 1 of this lecture, the ancient Greek culture that flourished starting several centuries BC. This man's name was Eratosthenes. He lived in northern Egypt, roughly around 240 BC. We know a few things about Eratosthenes today. For example, he was the librarian at the Library of Alexandria in northern Egypt. The Library of Alexandria is largely considered to be one of the world's first universities. He was essentially the headmaster, if you will, of that school. We also know him quite famously for the following measurement and calculation that I'm about to describe. Eratosthenes measured the circumference of the Earth using nothing more than a stick and a length of rope. Okay, so how did he make this measurement? Well, as I mentioned a few minutes ago, Eratosthenes lived in Alexandria, which is in northern Egypt. That town is still there today. Now, due south of Alexandria, in southern Egypt, there was a town at the time that was referred to as Syene. Syene is still there. Today it is called Aswan, Egypt. I assume on business that Eratosthenes periodically went back and forth between the two towns. Now, on a very specific day of the year, as observed from Syene, if you look at the sun at noon on June 21st, the sun is at the zenith. It is straight overhead. Now, due north in Alexandria, however, if you look at the sun at the exact same time at noon on June 21st, is the sun going to be at the zenith? No, it's going to be a little bit to the south of the zenith. Eratosthenes realized that you could make a couple of simple measurements and then use some elementary geometry in order to determine the circumference of the Earth. Here's ultimately how he makes the measurement. Okay, now let me go ahead and draw the Earth like so. And then let me also draw the following lines. Okay, what we're going to do is we're going to picture the sun here as being, for all practical purposes, infinitely far away. Of course, it's a finite distance away, but it's far enough away from us such that we can make this approximation safely. This then means that the sun's rays right here and here are parallel to each other. Okay, and then let's say that right here is the town of Syene. Here's how you spell that word, by the way. It's now June 21st at noon. And notice that if you stand here in Syene and it's noon on June 21st, the sun is straight overhead like so at the zenith. Okay, now let me also then draw right here, this point on my circle. This right here is Alexandria. It's further to the north than Syene. So notice that if you were standing in Alexandria, straight up towards the zenith is this dotted line right here. The sun's rays instead, however, at noon on June 21st are coming in on an angle. Right here is that angle. Let's go ahead and label that angle as theta. Now, because these two lines here and here are parallel to each other, this angle theta that I just described is the same thing as this angle here. And then on this diagram, this distance here and this distance here is equal to the radius of the Earth. The circumference of the Earth would be the distance all the way around like so. Let's refer to that distance there, that circumference, as c. Okay, now the first measurement that Eratosthenes has to make is he has to measure the angle theta. This is where the stick comes in. What he did is he stood in Alexandria. It's noon on June 21st. You take a stick and plant it vertically in the ground like so. That stick is pointing in this direction. However, the sun's rays are coming in on an angle like so, as seen from Alexandria. This then causes the stick to cast a shadow. The situation then looks like this. Okay, so let's say that this right here is the ground. We're in Alexandria at noon on June 21st. And then let's say that right here is the stick. This direction like so is pointing towards the zenith. That's straight up as seen from Alexandria. That's this direction here on the diagram above. And then we have the sun's rays coming in on an angle like so. On this diagram, the angle theta that I described on the top diagram, that's this angle here. Using some elementary geometry, this angle here and this angle here are the same thing, and then right here is a right triangle. Two measurements are made on this diagram. The first thing that you do is you measure the length of your stick. Presumably you know what the length of the stick is. I'm going to refer to that distance as A. And then this right here is the length of the shadow that is cast on the ground by the stick. Let's refer to that distance as O. Using a little bit of elementary trigonometry, which we'll get to a little bit later on in the course, ultimately you can find the angle theta. The angle theta turns out to be quite small when viewed from Alexandria. It's only 7.2 degrees. So Eratosthenes measures the angle theta to be 7.2 degrees. He uses some trigonometry to do so. Once again, we'll get to that a little bit later on. Okay, the next measurement that Eratosthenes has to make is the difficult measurement to make. That's the distance from Alexandria into Syene. Let's refer to that distance as S. So how do you measure the distance S? Well, Eratosthenes himself probably did not make the measurement. He hired professional surveyors at the time to do so. And here's what these surveyors had to do. They had to basically walk from Alexandria to Syene. And as they did, they took a length of rope with them. And they essentially then did the following. They started in Alexandria and they did this. 1, 2, 3, 4, and so on. And ultimately, by essentially pacing off the distance from Alexandria to Syene, I assume it took them several weeks to do it, they can then measure that distance. The distance is not trivial. In terms of modern measurements, the distance from Alexandria to Syene is 800 kilometers. That's several hundred miles. Okay, so Eratosthenes measures on the diagram above the distance S to be 800 kilometers. And now what we'll do is we'll just set up a simple proportion. So for example, on the diagram above, 360 degrees going all the way around the circle, that corresponds to the distance C, the circumference of the Earth. That's the unknown in this calculation. So the distance C corresponds to 360 degrees. The distance S, however, on the diagram above, 800 kilometers, that corresponds to the angle theta of just 7.2 degrees. So then therefore this ratio here on the left-hand side is equal to this ratio here on the right-hand side, where the distance S, remember, was measured by Eratosthenes to be 800 kilometers. And then therefore, the only unknown that remains here in this calculation is the circumference C, which we can now find. So let me go ahead and do some cross multiplying here and solve for the circumference. All right, so to do so, let me go ahead and first of all substitute the distance S here as 800 kilometers. So C over 360 degrees equals 800 kilometers divided by 7.2 degrees, like so. And now I'm going to just do some cross multiplying here and then solve for the circumference C. All right, so on my calculator, I first of all have 800 divided by 7.2. And then cross multiply the 360 over. And then therefore, the distance C on the diagram above, the circumference of the Earth, is exactly 40,000 kilometers. Now, how does this compare with the actual circumference of the Earth, which we know to a high degree of accuracy today? Well, as I mentioned in part 1 of this lecture, as the Earth rotates, it bulges a little bit at its equator. So this then means that if you measure the circumference going around the equator of the Earth, it's going to be a little bit bigger than if you measure the circumference going all the way around what is referred to as the polar distance around the Earth. That is from pole to pole, for example, like so. However, if you take the average of the two, the Earth's average circumference is 40,074 kilometers. So once again, this number today we know to a high degree of accuracy. More than 2,000 years ago, however, Eratosthenes arrives at a result that is extremely close to today's currently accepted value. Eratosthenes will be remembered forever for this calculation. And the reason for that is because his measurement, this calculation, is an example of what is referred to as an elegant solution in physics and in science in general. A solution is considered elegant for the following reason. Imagine more than 2,000 years ago. There's virtually no technology. And then Eratosthenes comes along and he realizes that he can measure the size of the Earth by using just a little bit of elementary geometry and a couple of basic measurements. That's an extremely elegant solution to a seemingly extremely difficult problem more than 2,000 years ago. Okay, this concludes part 2 of this lecture.